Is Unit 2, Lesson 5. So the first thing you should do is look for the tasks to complete for U2L5, either under assignments or in the weekly calendar on the Canvas homepage, as we usually do. As usual, we're going to start off with just kind of a silly little share question. So remember to say hi, check in with the person that you end up being partnered with, and share your answer to the question I'm throwing in the chat right now. Today's question is, if you had a time machine, would you go back in time or into the future, and why? And let's say that you're just visiting. So the main thing is you're visiting. So you go back in time and come back to present, or go forward in time and come back to present. But it's more of a visit question. Give you 20 seconds to think about it and then throw you into breakout rooms. Okay, we'll come back together in 2 minutes. Rooms are open. The homework, all you had to do was make sure you have posted to the how far you can throw Flipgrid. I'm seeing 11 responses to that. So remember, you just have to record one set of throws, just one balled up sock and one loose sock, and make sure you've completed that quiz. Otherwise, the other 2 quizzes look pretty good. The one was on the PhET simulation. The other one was on the last section at Hewitt, chapter 5.12, all about orbits, which we're going to be exploring through at least the next 2 lessons. Any big questions or anything you got stuck on those assignments or needed help on?
Just that it like snowed 14 inches over the weekend, so I wasn't able to go outside and do it, but today it's like melting, so I'll have it done by tomorrow.
Okay. Yeah, and again, the reason I did like a sock too is that you could, if you've got a long enough hallway or something, you could theoretically do it inside too. But outside, it is nice to just get out and do something as well. So that's cool that you got a little snow over there. The big takeaways I would say from these assignments, one thing, if you fire a projectile at, let's say, 30 degrees and 60 degrees, note that those both add up to 90 degrees. What might be true about where those projectiles land? Anytime you have 2 angles that add up to 90, what can you say about where the projectile lands? Nathan?
They'll land in the same spot.
Yes, so that's one of the key trends to take away from the reading. However, that trend makes 2 big assumptions. Can anyone tell me at least what one of the assumptions is for that to be true? Abby?
There's no like air resistance or
Yep,
drag.
so 0 air drag, and there's something else too about where it's fired from and where it lands. What else has to be true about the launch point and the landing point?
It's like not curved or anything. It's horizontal angle.
Yes, that they're both basically at the same elevation, right? That the projectile where you fire it from is also where it lands. Any deviation from that 90-degree angle thing doesn't work anymore. So just keep that in mind that it's pretty limited. You also had to figure out, why is the statue of David pictured at the base of the cannon? Anyone got any ideas?
I said it's like comparison to like the size and distance, like to like a real human size.
So they just put it in for scale. How many people have been to Florence and seen the statue of David? Anybody? Clarence, is David proportional to what a human being is actually sized? No, the statue is almost 2 stories tall. That's one of the things that's amazing about it, is it's just enormous. Ryder, I saw your hand up. Any ideas?
No.
Okay. So who knows their Bible? Does anyone know? Abby, you got an idea?
That was my idea. Oh.
All right. Abby, what are you thinking?
Okay, so I'm pretty sure that David and Goliath, like David beat the monster Goliath by, I think, like slingshotting rocks or something. Like it was like his trusty slingshot, and that has to do with projectiles. And I think that's like the comparison.
Yeah, that's why they did it. He threw a projectile. So, and again, if you've seen the statue of David, he has his hand up over his shoulder, and he's actually holding sort of like a leather sling, which was kind of, he'd spin it and throw a rock. And yes, that is how he defeated Goliath. So that's why they have that there as a reference. Took me a while to kind of figure that out too, because Joseph, like you were saying, I thought it was just there for fun or for scale, but I was like, oh, wait a second, it is projectile related. So talk about nerdy. Okay, that was it for homework stuff. Next on the task then is just a quick reminder about Canvas. I have been getting some questions about where to locate certain things. So just a quick reminder, if you don't know this already, if you go to the Science2 homepage, there's just two things I want to point out. If you're curious about where recordings of classes are, like if there's videos, those are all on the homepage in the weekly calendar. I've been recording every single lesson, and I'm a little behind right now, but for the most part, there are video recordings of pretty much every lesson on there, and they're in the same column with the plan. So if you look at it's the in-class one. So any plan link right there, so like Science2C, Unit 1, Lesson 4 plan, that's your tasks to complete list, and then I've got the video links below there. So you can always go there to find videos of our lessons. There's also homework summaries and things like that. And then in this menu bar here on the left, you'll see there's a tab for grades. If you click on that, it brings up a summary of all your assignments. It shows you what's missing. It shows you any notes from me. And if you scroll all the way to the bottom, you can see your grade as it currently stands. And that is what is going to be reported once, I think later this week, once grades come out. So feel free to check that out and let me know if you need help on anything. Any questions or comments on that? All right, our goal today then is to explore some orbit stuff and get you drawing and maybe using an online simulator. But first, we're gonna start with a little clip from a TV show called Family Guy. Any Family Guy fans out there? All right, it's only 40 seconds long, so here we go. I'm gonna pull it up, and then you're gonna answer some questions related to it. Gonna optimize the screen here for sharing, should be good. Okay. Here we go.
Peter, I think maybe you're in denial about this fat thing.
Oh, yeah? Well, I challenge you to prove to me that I'm fat.
Okay, hang on. See this?
Yeah?
You know what it is?
Duh, it's an apple.
Good, good, good. All right, watch this.
What the hell? What is this? What is this, some kind of gag?
No, that's orbit.
Huh?
You have your own gravitational pull.
Oh, that's a bunch of crap.
Now back to the Three Stooges.
Aw. Aw.
All right, on the tasks to complete list, there is a short Google form that I would like you to complete based on that clip. You can watch it again if you need to, but I'm going to time for 5 minutes to complete the form. Again, it's step number 4, titled Intro to Gravity Family Guy Clip Google Form. Go for it. You'll notice that Brian actually throws the apple, right? And he kind of launches the TV and things like that. And it's because in order for things to orbit, they have to have tangential velocity, right? They're not floating, they are falling around that object. And so the idea is that if he had just held the apple next to Peter and let go, the apple would have just fallen against Peter's belly, right? If he had his own gravity. But by throwing it sideways, it's within Peter's gravitational influence, but it's got the tangential velocity to float around it. Again, I'm probably thinking about this way too much, but that's how it would work. In short, he's saying you have your own gravitational pull. Why is this technically a flawed argument? Very good. Most of you got that it is because everyone exerts their own gravitational pull, right? If you have mass, then you are exerting a gravitational pull on everything around you. But the last question gets at why this isn't a big deal. And it's the correct answer, which again, looks like we're pretty torn here. But it's that the gravitational constant G is an incredibly small number. If anyone remembers, it was some number times 10 to the negative 11. This is what brings newtons and force into the equation. And it's just sort of putting it in context, right? That gravity is actually extremely weak. And so we only see gravity really influencing strongly very large objects like planets that we're on, right? We can sense gravity pulling it down. What we exert on things is negligible, but is there, right? There's no such thing as no gravity at all. Any questions or comments on that? All right, so again, we're gonna be talking a lot about orbit. I'm gonna highlight my screen here really quickly. So we often see orbits pictured like this, right? We've got some kind of star or center of gravity and you've got objects floating around it. This is my attempt at drawing a circle. But what I wanna emphasize with this is, and according to this chapter you just read in Hewitt, Do most objects actually orbit in a circular pattern? Good, I'm seeing shaking of heads. They don't actually. Does anyone know what shape orbits actually tend to be?
Is it an oval?
So you bring up a very good point here. Technically, the term is not oval.
Ellipse.
Good, ellipse, an elliptical. But whoever said oval, it's good thinking, right? Because this is how I used to think of it too. What I want to emphasize is that an oval is sort of like an egg shape, right? Where it's a little rounder at the base and sharper towards the edge. Again, that's kind of like an extreme oval, but that's what I think oval is actually referring to. And that's not how orbit works, but that is exactly how I used to think of it too. And so, yeah, you have to think of the term elliptical. What makes an ellipse difference is that it's sort of a circle that's been flattened, but it's much more even. You don't have a wider edge and a sharper edge, even though I can't really draw it that way. But this is what an ellipse is. And so there's a way of actually measuring how round an ellipse is, and we call that the eccentricity. Eccentricity. And eccentricity is just a small number. It's like 0.2, or it might be like 0.8. But the point is that the closer to 0 eccentricity is, the more circular your ellipse is. So a very circular ellipse would have a low eccentricity. A very elliptical ellipse, so like the one I have drawn here, really flattened, would have a very high eccentricity, like closer to 1. And you're going to see how to calculate that. It's just a simple ratio of two different measurements that you take. You can calculate circumference, though, if you're messing with a circle. And this I'm hoping most people know, but if you had a circular orbit and I asked you to calculate circumference, does anyone know the equation for circumference? Remember there? 2 pi r. Who can give me the value of pi? Just 3 digits.
3.14.
Awesome. And what does r stand for?
Radius.
Good. Distance from the center to the outermost edge. So you'll do a little math with that, and you'll do a little math with eccentricity. I have a short video on the tasks to complete list that kind of talks through all of that I just went through, so feel free to watch that if you want. There's also a demonstration video on the assignment you're about to do that walks you through all that too. So I'm hoping you'll be able to figure it out. Okay, so the big activity is then you're going to create a drawing. You're going to need a push pin and some kind of string or floss. You'll need a ruler and a couple other things, but all of that's listed in the assignment. This is step number 5, titled Do Some Math. You're going to be calculating details about orbit. I'm going to time for 20 minutes to work on this, and then we'll come back together to check in on how we're doing. I'll be here listening if you have questions, if you're not sure what to do, or if you're not sure like what equipment to use. Go for it.